So our next lecture series is by Phiala Shanahan, professor at MIT, and expert in Lattice QCD, and we'll tell you well, everything she can in 2 lectures about it. She has a long list of distinctions that you can read about in her Wikipedia page, which apparently is more well developed than that of Fermion, including the APS dissertation award in hadronic physics in 2017. She was one of the 30 under 30 featured in Forbes magazine, which must mean she's making tons of money from Lattice QCD. And was recently awarded the DOE Early Career Award, and as well as the APS's 2021 Maria Geppert-Meyer Award. And we're very pleased that she will give us what promises to be a beautifully written lecture over Zoom for you on Lattice QCD. So yeah, thanks for giving us these lectures in this format, and take it away.
Well, thank you very much. It's great to see so many faces there, and I'm really sorry I can't be there in person. All right, so we've got 2 lectures, right? 3 hours to have an introduction to Lattice QCD. So my goal is obviously not to go through all the gory details to a point where if you've never seen Lattice QCD before, you can go and run a calculation. My goal is really going to be to focus on the intuition, so that if someone says they've done a calculation with a HISC action on a 24 by 48, 24 cube by 48 box, and this is what the data looks like, you know whether that's what it should look like and what that all means, and some, know what's easy in Lattice QCD, what's hard, and why. And so that's really where we're going. So we'll go through that in 5 stages. Lecture 1, I hope to get through this. So why Lattice QCD? Anyone want to give me the answer to that?
Maybe ask her to lower her mic volume, because I don't think we can fix it here.
Oh, sorry. Can you not hear me?
It seems distorted. Maybe you can lower your mic volume.
A little watered down.
Okay, let me see what I can do. How about that? Is that better? Testing, testing, hello.
Maybe lower it a little bit more.
You lower your mic and we'll raise our speaker. I think that will sound better.
Okay, how about that?
That's better. Is that better? Okay.
Okay. All right, can you hear me now?
Sounds good.
Thank you.
It sounds great.
Okay, very good. So I was saying that we want to start with, the why of Lattice QCD, some of the definitions, so we get the notation on the same page. And I mean, for section 1, the why of Lattice QCD, does someone want to give me the answer to that, even before we get started?
We use Lattice QCD because there are certain situations where perturbative methods don't work.
Yeah, exactly. The answer is that QCD is non-perturbative.
And experiments are very expensive.
Yeah, good. Okay, so that's why Lattice QCD. Now we're going to define the notation and discuss further. So this is really this first section is really an excuse to get all of the notation right, because we need to make sure we have all of the spaces. There's lots of different things going on, flavor, color, spin, and so on. We need to make sure we have all of that under control, because when we want to define our lattice actions, otherwise things will get very confused if we can't remember what spaces everything's living in. So the QCD Lagrangian, of course, should be pretty familiar by this point in the school. Okay, so d slash, of course, is d mu gamma mu. We have different quark masses here. F is indexing the fermion flavor. All right, so let's just break this Lagrangian down a little bit. So the quark fields here, the size, what are all the indices on the size that I've been ignoring? Because when we put this theory onto a discrete space-time lattice, which is how we're going to formulate lattice QCD, of course, we need to make sure we keep track of all the right degrees of freedom. So we've got quark degrees of freedom, which we had psi f. So what indices did I, not write down explicitly in the QCD Lagrangian up here on the size?
Colored charges?
I'm sorry?
Colored charges, is that what you're missing?
Yeah, okay, so we want a C for color. Good, what else?
Spin.
Yeah, we have a Dirac index. What else? Maybe an argument?
Someone said position.
Yeah, exactly, thank you. Space-time, right? It's a field. So we've got flavor. So the flavors, of course, come in this selection here. So when you're doing a lattice calculation in QCD, it's really the up, down, and strange, which are in some sense the default. The top quark, it doesn't hadronize, so we pretty much never worry about that in lattice QCD. And then the charm and the bottom are sort of tricky, and there are different ways of getting those into your lattice QCD calculation. So the reason that they're tricky is that, as we'll see, you get discretization errors. So errors from the fact that you have a finite lattice spacing, which go like that lattice spacing times the quark mass. So when the quark masses get big, like the charm and bottom masses, those errors from having a finite lattice spacing get big too. So you either have to go to really fine lattice spacings to use the same sort of tools that you would use for the up, down, and strange. And we'll go into a little bit of detail later on why fine lattice spacings are hard, or you have to do something a bit different. So you could do things like a heavy quark effective theory. You could use a non-relativistic QCD action just for those quarks. So these are tricky discretization errors proportional to A, which is the lattice spacing, times MQ. So if there's a charm quark in a simulation, for example, it could either be done fully dynamically in the same way as the up, down, and strange, or there could be something else going on, like a heavy quark effective theory. Okay, the other indices we've got here, so we have alpha, that's a Dirac index, okay, which run over 1, 2, 3, 4. And we have C, which is a color index, which runs over 1, 2, 3. All right, so that is our quark fields sign. We also have here in this here is really the fermionic part of the Lagrangian, that's the part with the quark fields in it. We also have some gamma matrices appearing. So these are the Dirac gamma matrices. So of course, they're elements of a Clifford algebra. So they have this commutation or anti-commutation relation, gamma nu equals 2g mu nu. Okay, so I guess I've been working from the assumption that everyone has at least some vague idea of what lattice field theory is going to be. Maybe I should have said this at the start, but we're going to discretize the theory of QCD onto a finite four-dimensional space-time grid in Euclidean space-time in such a way that we can do calculations numerically without having to use perturbation theory. Okay, so the discretization we're coming to right now, the Euclideanization that we'll get to is already sort of rearing its head, because when we want to write a Euclidean version of this, these gamma matrices will have a different anti-commutation relation. So when we go to Euclidean space, we'll have to write down Euclidean gamma matrices, and this will look like 2 delta. instead of 2G mu, right? And mu and nu here are, of course, in 0, 1, 2, 3, or 1, 2, 3, 4, depending how you index. So these gammas are, of course, 4 by 4 matrices. Many different bases will be okay. And thinking to lattice QCD, the only difference that you have to worry about is that you need a Euclidean basis of the gamma matrices. Okay, so we've got quarks, we've dealt with the gammas. The other thing that we see in this expression here, hiding inside these Fs, of course, are the gluon degrees of freedom. So we have A, mu A, also, of course, a field. So we're putting that X label, that space-time on there. We also have a Lorentz index. So we've got, and we have a color index. What does the color index run over for the gluons?
There's a eight gluon colors, not that much.
Exactly, thank you. So runs over 1 through 8. All right, this gluon degrees of freedom here, typically we'll write this in terms of a matrix valued field, right? And we'll write these color degrees of freedom in that matrix and drop the index. So we'll typically be writing down just A mu, which is defined as these components times these TAs, which are the generators of SU3. Which you can write, for example, in terms of the Gell-Mann matrices here, lambda A over 2. And these, of course, you could express, for example, as 3 by 3 matrices, right? So lambda 1 is 0, 1, 0, 1, 0, 0, 0, 0, 1, etc. Okay, so far nothing different from the continuum QCD that you've had a few lectures on. These generators, they satisfy, the SU3 algebra. So their commutator looks like I, F, A, B, C, T, C, where that's the antisymmetric structure constant, all the regular QCD stuff. Okay, so here we have the gluon degrees of freedom in terms of A. Here they are in terms of F mu nu. So last bit on this sort of reminder of QCD is, of course, that we get these fields A when we build covariant derivatives, and then we build the gluon field strength tensor out of these gluon fields A. So covariant derivative looks like this. We have this G coming in here, so this coupling. This entire expression here, what sort of an object is this? Is this a scalar? Is it a vector? Is it a matrix?
Matrix.
Right, this whole thing's in matrix notation, right? Which we'll be using throughout. Okay, and then the gluon field strength tensor. Looks like the commutator of our covariant derivatives, which again is defined in this matrix notation, right? So we could write out the components F mu nu A with the color index explicitly times these generators of SU3. Okay, so the whole reason QCD gets interesting and non-perturbative, we can basically read off the Lagrangian itself, that it has gluon self-interactions like we don't have in QED, which generates a lot of the interesting features of QCD, especially asymptotic freedom and then confinement through the running of the coupling. So if we just remind ourselves what those look like, we have the gluon coupling to the quarks, we have gluon self-interactions like this. And we just don't have diagrams like that in QED, right? And this is what makes it all so interesting. All right, so at this point, we've just defined our Lagrangian and reminded ourselves of these gluon self-interactions, which is sort of a long-winded way of getting back to the answer that we gave right at the start of why worrying about lattice QCD. In that, if we think about the coupling versus our energy scale, and just sketch it here. There's some nice easy numbers here that at about 1 GeV, we have our coupling is at about 1, and then it goes down to about 0.1 by 100 GeV. So over here, we have asymptotic freedom. And up here at low energies, the coupling becomes large. So this running of the QCD coupling with energy, which is really a result of the quantum effects, gives us this thing here, that at low energies, the coupling gets large. We can't expand in powers of the coupling anymore, right? When it's large, squaring it doesn't make it smaller, so your perturbative expansions don't work. And so then we need lattice QCD for low energy QCD. So running of the QCD coupling. Which is, of course, related to this coupling G that we saw here. Okay, and so if we want to study anything in QCD at low energy, we're not going to be able to do perturbation theory, but it's actually more than that, right? It's that we have that physical quantities are not actually even analytic in the QCD coupling necessarily. So that they're not even necessarily given by a convergent power series locally. So then where QCD is non-perturbative, we're really, we're left with numerical tools like lattice QCD. So before we go ahead and try to put this Lagrangian onto this discrete space-time and see how that works out, we need to think for a moment about the symmetries, because it'll be important to think about whether we're preserving them or not, and in what way, when we change the theory onto a discrete space-time. So what symmetries do we have in QCD? Anyone? And it's a bit hard to do this, discussion, because I know you guys aren't near microphones, but anyone want to shout something out?
SU3 color.
Okay, thank you. We have an SU3 symmetry. So SU3 gauge symmetry. Yeah, and you called it SU3 color, that's right. It's basically local rotations in color space is what the SU3 gauge symmetry is, right? That means that our quark field here, psi x, where now I'm dropping all of those indices, but we know they're there, is transformed like this, where what I've written here as this transformation matrix, called an omega here, is basically doing exactly that, a local rotation in our color space. So these things theta are just parameters, parameterizing the transformation, and these TAs are again the generators of SU3 that we saw before. Okay, so just looking at this parameter here, theta, it's labeled by an A, That's because we can have a different parameter for each of these SU3 generators there, remembering those go from 1 to 8, and they can also depend on the space-time x. So that's the local rotation in color space, right? And so that's how the quark fields transform. The gauge fields also transform under this symmetry like this. Which looks sort of a bit ugly, but if we look at the field strength tensor instead, of course, that has a much simpler transformation under this SU3 gauge symmetry. So F mu nu transforms just like the covariant derivative. Okay, so when we discretize this theory, we're going to have to worry about our SU3 gauge symmetry. What other symmetries do we have?
RM.
Yeah. So we have a Lorentz symmetry, basically, right? And we have C, P, and T, if you like. So you might already guess that the Lorentz symmetry, when we go on to a discrete lattice, will be broken to the shape of the lattice. It will be broken down to a hypercube, for example. And so that's one of the challenges in Lattice QCD, is that the breaking of that symmetry group down to AH4, the hypercubic group, will induce mixing between some operators under a normalization that wouldn't have mixed in the continuum. And so that's why, for example, things like moments of part-on distribution functions, if you go to higher and higher moments, eventually they start getting very, very difficult to get from Lattice QCD calculations, because you end up trying to calculate operators that mix in power divergent ways in the lattice spacing with other things. Okay, so we'll see more about that later. We also have a U1 global symmetry, right? So we've got basically a U1 rotation, right? Parameterized here by alpha. And then we have another bunch of symmetries which happen only in the chiral limit. So the chiral limit is when all the quark masses vanish, right? So chiral symmetry, if you like. Okay, so chiral symmetry is particularly important to mention when we're talking about Lattice QCD, because we'll see just a little later in this lecture that when we try to discretize our QCD Lagrangian, discretize the action, that we end up not being able to necessarily preserve chiral symmetry in the right limits very easily. And so that means that you're left with choices, as we'll see when we go through our discretized fermion actions, that you can choose to, for example, give up getting the right chiral symmetry in the limit as the masses go to 0. And for applications where that's not very important, maybe that's a sensible thing to do for the return of saving computer time versus trying to preserve as much of the chiral symmetry as you can, but doing a much more expensive calculation. So in the chiral limit, we also have for example, a global invariance under axial transformation. So that's the U1A symmetry. Okay, what does a global axial transformation look like?
Like the U1 with the gamma 5 in the exponent.
Yeah, exactly. Thank you. So just like our global U1 vector, whoops, there's a sign missing. If you notice me making a typo, please shout out. Okay, and so we're gamma 5 here, right, that's of course I, gamma naught, gamma 1, gamma 2, gamma 3. It's defined the same way in Euclidean as it is in Minkowski spacetime. Okay, we also have global flavor rotations, right, where we're going to include flavor matrices acting in flavor space up here. So okay, so here the taus, those are the generators of SU and F in the fundamental representation. So for NF equals 2, what are the taus? You have 2 flavors. They're Pauli matrices, right? For 2 flavors. What about 3 flavors?
Kelman.
Okay, great. Thank you. Okay, so what we're left with is SUNF vector. That's this one. SUNF axial. U1 vector. That was this one up here. U1 axial. Okay, and of course we know that not all of this is manifest in QCD. The U1 axial, for example, that's broken by the axial anomaly. So the fact that the vacuum is not symmetric under this transformation. Of course, this here, that's spontaneously broken. That's Goldstone's theorem, the fact that you get NF squared minus 1 massless excitations. That's the spontaneous symmetry breaking here. And the fermion mass, of course, explicitly breaks chiral symmetry. Okay, so, you know, we don't have chiral symmetry, right? So you might be wondering why I'm talking about it at length here when we're talking about putting QCD on the lattice. But you want your theory to be right in all of the right limits as well. So you might want that as you take the limit, as all the fermion masses go to 0 and chiral symmetry is restored in the continuum, you might want the same sort of behavior in your numerical simulations as well, right? So, and different ways of putting the theory onto a discrete space-time will have very different outcomes in terms of what it means for chiral symmetry and whether you've preserved it or not. Okay, so that's our theory. That's our symmetries. Now we're going to put it on a discrete space-time. So what the lattice regularization really gives you is a way to describe non-perturbative QCD in a systematically improvable way. Now, anyone want to guess what I mean by systematically improvable? That's really the important thing here. Okay, so by systematically improvable, what I mean is that you get back to QCD when you take all of the limits that you need to take. So you have a discrete lattice spacing on some finite box. You take the limit as the volume gets large. You take the limit as the lattice spacing gets small. and you do calculations with smaller and smaller spacing on bigger and bigger volumes. And then you can extrapolate and you expect to get back to QCD. So on any fixed calculation on some fixed volume and spacing, you're going to have an answer that's not continuum QCD, right? But it's systematically improvable in that you can get closer and closer to continuum QCD by stepping closer and closer to those limits. So we'll see much more about these later, but we're talking about lattice spacing going to 0, the lattice volume. Going large, and so on. Okay, so the other very important thing about what we're talking about here, which is just taking QCD and trying to put it on a discrete spacetime, is that the free parameters in the lattice formulation of QCD are the same as the free parameters in QCD itself. So in that Lagrangian that we had up on the previous board, we had the quark masses and we had the strong coupling, right? And that's it for free parameters. So the same is true for the lattice formulation. And once we fix those, everything else you calculate from TMDs for the proton up to nuclear reactions, they're all going to be predictions from QCD without any additional input, without any modeling of a nucleus as protons and neutrons. You've just got the same free parameters of QCD. Okay, so important application areas of lattice QCD then. So I'm going to post after this a sort of prettier copy of these notes, and I'll put in some more details in there. But important application areas are going to be anything at low energies, anything where perturbation theory is not going to get you the answer you like. And in particular, anything that you can formulate in such a way that it's calculable in your Euclidean formulation. So anything with, real-time dynamics is going to be hard. Anything involving light cone separation is going to be hard, but as you'll hear in say Michael Englehart's lecture tomorrow, is it tomorrow? Maybe the day after. There are ways of getting around that. But anything where you can formulate your question in terms of matrix elements in a Euclidean spacetime, lattice QCD will work very nicely. So let's say thermodynamics is one really important application area. So the QCD phase diagram versus temperature and density and chemical potential mu, you see a crossover to the quark gluon plasma at some critical temperature, something like 150 MeV. And so an exploration experimentally of that is a major goal of the Wick program at Brookhaven. And you're able to get a lot of the basic thermodynamic quantities of high temperature QCD out of lattice QCD calculations as well. There's precision flavor physics. So that is trying to constrain parameters of the standard model that encode quark mixing, so the CKM matrix. So you want to constrain the CKM matrix parameters because you can then use those to make predictions of other processes, things that might be really rare, or things where you might be able to search for beyond standard model physics if only you had a standard model prediction to compare the experiment with. And so lattice QCD is incredibly important in constraining that. In hadron spectroscopy, so some of those basic questions of low energy QCD, can we understand the spectrum of particle states directly from the standard model, like the mass of the proton? And through Lattice QCD, we can. In the last maybe 5 or 7 years, we've been able to do calculations of, say, the proton-neutron mass difference and see how that comes from the delicate cancellation of the strong QCD pushing that mass difference one day, and electromagnetic interaction, so QED pushing it the other way. And you get the cancellation that gives you exactly the proton-neutron mass difference that you can measure experimentally. So experimentally, you can measure the difference, right? But from theory calculations, you can really see how that difference emerges through cancellations in the theory. There's things like beyond spectroscopy, hadron interactions and nuclei. So how do hadrons interact? How do you get nuclei directly from QCD? How do nuclei interact with electroweak currents or BSM currents? And I shouldn't neglect to mention that beyond the standard model, Lattice QCD can also play a really important role, that there's many interesting field theory questions beyond the perturbative regime. Say Technicolor, so looking at strong dynamics at the electroweak scale. These are things that you can try to calculate in Lattice QCD as well. Okay, so this was really sort of a long-winded why Lattice QCD and reminder of what QCD is, so we know what we're going to try to put on our discrete space-time lattice. Okay, so now, how do we do that putting? So this is really the second part where we're going to think about Euclidean discretized path integrals. So hopefully, most of that previous, I know we went quite quickly, all the QCD stuff's familiar from some of the other lectures in this school, but any questions, any bad typos that were confusing, anything like that? Okay, cool. So as you probably get from this title, where I say Euclidean discretized path integrals, lattice field theory is really built around the path integral approach to field theory. So let's think about path integrals in field theory. Okay, so in the path integral approach, we know that the generating functional contains all of the information about the theory. If you can compute that, you know everything, right? So generating functional contains all info about the theory. And the generating functional can look something like this. So here I'm writing down our path integrals. And we have the exponential of the action here. Okay, so here, these things here, these are source terms that we've added to the action. Here, these is of course our path integral. So that's integrals over all possible gauge and fermion fields. Okay, and why this generating functional is so useful is, of course, that expectation values, if you like, Green's functions, correlation functions, they can all be expressed just as functional derivatives of this Z thing, right? So so if we wanted to take the expectation value of some series of fields, so some endpoint correlation function here, this just looks like 1 over Z, and then a whole bunch of functional derivatives pulling down each of these fields. Okay, we need to remember, of course, fermion fields, anti-commuting, right? So the psi's and psi bars here, if we're writing down an endpoint correlation function, we have to remember that they're, Grassmann number valued fields because they're fermions. And then this is really something that we'd like to compute. And to compute this, we have to define and interpret the measure here. Right, we have to define what this means to do these integrals over all possible gauge and fermion fields. And we also have to regularize momentum integrals. And the lattice regulation really gives you a way of both defining the measure and regularizing the momentum integrals. So in perturbation theory, if you start with this, how do you calculate something? You basically just do a perturbative expansion, right? You perturbatively expanded and powers of all the couplings. So that's not what we want to do if we have non-perturbative physics. So we need to define this directly. So perturbation theory, we're going to expand Z or correlators in powers of the coupling. And instead, we want to define Z directly in a way that's valid beyond perturbation theory. So we're going to define it directly through a lattice regulator, which just means we're going to discretize the theory and put it on a lattice. And this gives us not just a definition, and actually probably this is how the path integral was defined in whatever field theory course you took, that you defined it on some discrete space-time and took the limit as that spacing went away. That was probably the definition you used. But it also gives you a way of doing direct calculations. So this gives us a numerical evaluation approach. Okay, so before we write this down on a discrete space-time, we're not going to do it with in Minkowski space. So probably when you did this in your field theory class, you did put it on a lattice, but you probably just left it in Minkowski space for that definition. So that's not great for numerical evaluation though, because we have this essentially oscillatory integrand. This is e to the minus I s QCD, where s is the action. So you get cancellations between different regions of phase space because that's oscillatory. And so that then gives you numerical problems. And so that's why we're going to actually first move to Euclidean space-time. So do a Wick rotation and then discretize the theory. So the oscillatory integrand from e to the minus SQCD gives you cancellations and problems. So what we're going to do is we're going to Wick rotate. So we're going to send t goes to minus I t Euclidean from Minkowski to Euclidean space-time. Okay, so that's going to get rid of the I here. And we also have to remember to change our gamma matrices to the Euclidean gamma matrices, right? So the anti-commutator now has the delta function instead of a G mu. So this is useful because we now just have a probabilistic interpretation of the functional integral. Okay, so what we have is we have e to the minus I SQCD has gone to e to the minus SQCD, right? So this exponential here, that's just exactly the Boltzmann weighting of a statistical ensemble. Right, so now the problem just looks exactly like StatMech. And it gives us something that we can do efficiently numerically. Okay, so we've Wick rotated this thing. This I goes away. We're now in Euclidean spacetime. Now we need to put it on the lattice. We need to discretize. So we're going to discretize the theory. So you can do all sorts of things with discretizing the theory. We're going to do the simplest thing right now, which is onto a 4-dimensional cubic lattice. It is most common to use essentially hypercubes, but it's also very common to have one dimension, say, longer than the others, or you might have the lattice spacing different in different dimensions, which is useful for different applications. As you'll see, a lot of things depend on the lattice spacing or the time extent. And so if for a specific application, it's really important to have the lattice spacing small in just the Euclidean time dimension, you can create a lattice that has a smaller spacing in that dimension, for example. But for now, let's just think about a hypercube. So we're going to restrict ourselves to this hypercubic grid of points where this A here, that's the separation between the points, has the pretty obvious name of the lattice spacing. It's the spacing between the points in the grid. Okay, so I've defined this as an infinite lattice, just for convenience right now. Of course, typically in practice, you have some finite extent of your lattice, and then you'll have some boundary conditions around the edges. So typically, they'll be anti-periodic for fermions and periodic for everything else. So typically you'll see that finite extent written as something like this, L cubed times T. So that's because it is very common to have a different extent in the time direction than in the space directions. And so the L cubed here means you have L lattice sites in each spatial direction. So some number like 24 sites, right? And some other number in the temporal direction. Okay, so we want to put our theory on the lattice. We started with quark fields, which were defined at each space-time point. Right, so quark fields. And the simplest thing to do is to say, well, we're going to define our quark fields instead of at every point in space-time x, just on the sites of our lattice. So this n is living inside, or this is the set of all sites of the lattice, and we're just going to define our quark field on those sites. Okay, a few other things need to be discretized. So we had a d4x here, right? d4x. Now we have just a finite set of sites. So what's that going to go to? Yep, that'll go to a sum. What about a path integral? What does that go to? So this is, like I said, probably how path integrals were defined in whatever field theory class you've taken. What was the limit of this?
This is going to have spin and color indices on every site. So for every spin color combination, it's going to be a complex number.
Yeah, so good. I'm going to ignore spin and color just to, but you're right, just to make our lives easier and think about just the site part of it, so the part coming from the discretization here. So we're going to have our separate integral here, so a d psi n for each site of the lattice here n. So if you know, in your field theory class, you probably had, you know, your path, at least the way we teach it here, we start with quantum mechanics and we say, okay, here's some path, could go into an arbitrary place, but we're going to discretize and say that it has to move between, you know, our discrete set of points. And then you integrate on each slice. And that's exactly what we're doing here, except in higher dimension tensor vector. Okay, so that's how the quark fields discretize. That's easy. The gauge fields, we'll see soon that it gets a little more complicated, but I'm going to come back to that. I'm going to sort of tell you the answer that we'll see in a minute, because I want to give you the broad idea of lattice field theory before we get too much into the weeds. So we'll see soon that to maintain gauge symmetry, in the discretized action, it's convenient to define gauge link variables. So gauge links are parallel transporters between neighboring sites. And like I said, we are coming back to this, but instead of our gauge field A, we're going to find it useful to move those degrees of freedom into these things that we'll call U, which are essentially parallel transporters. So think about starting at site N here and moving to site N plus mu times your lattice spacing. And the parallel transporter that takes you from one lattice site to the next lattice site can be defined like this in terms of those gauge fields. And that is what we'll see are the most convenient degrees of freedom for our discretized gauge field. So we'll come back to this. I wanted to basically get to our quark fields go on the sites. We have some discretization of the gauge fields, and then what the basic idea of lattice QCD is in terms of all of these degrees of freedom. So the basic idea of lattice is that we want to calculate something, the expectation value of some operator, some endpoint correlation function. And we know what that looks like in terms of a Euclidean path integral. Okay, so we've integrated here over our gauge fields, which we're now writing as U, because I told you we're going to end up in terms of these parallel transporters. We have our quark fields. We have e to the minus s of the action, because we're in Euclidean space, there's no I. And this is whatever thing we want to calculate the expectation value of, right? Our QCD action looks like some gauge piece plus some fermion piece. So this thing that's, you know, minus a quarter f mu nu, right? This is just a quadratic way of writing out the fermion piece in terms of what we'll call the Dirac operator. There's just a rearrangement, which we'll do explicitly in a moment. And what we can do then is we can explicitly integrate out the fermions, because this thing here, it looks quadratic, it looks like a Gaussian integral, right? And we know how to do Gaussian integrals. So you can integrate out the fermions to get an expression that looks like this. And so we now only have the path integral over the gauge fields. Integrating out the fermions gave us the determinant of this matrix. Again, just think about a Gaussian integral, you get something pretty similar there. We're left with just the gluon part of the action. So that's the f mu nu piece. And then our observable has been rewritten in terms of U, and instead of the quark fields, it's been rewritten in terms of these M, these inverse Dirac matrices. So what we've done here is first integrate out the fermions. And then we have to interpret what this measure is. So we're going to go onto a discrete finite volume. So we're going to discretize and compactify that measure. So discretize and so some finite volume. With some boundary conditions. So what that means is that this du is going to go to, let's be really explicit, just like we did for the fermions, but I'm now going to put in all of the extra degrees of freedom too. That we have the product here over mu. That was our, that's our direction, right? A is our color. This sum over n is over all of the points in our discrete volume. And what we then have is a large but finite dimensional integral, right? And the dimensionality of that integral depends on the size of your finite space-time volume, depends on the number of colors, and it depends on your dimensions. So okay, so this is then something, it's just a really high dimensional integral to give you a sense of the scale of that integral, which we'll focus a lot more on that in the second lecture, is typically, you know, this total number of degrees of freedom will be really, really large in state-of-the-art calculation, something like 10 to the 9 to 10 to the 12. So you're doing a really high dimensional integral numerically, right? Which means that just trying to integrate without doing anything, you know, if you just try to, you know, blind Monte Carlo integrate, that's not going to work in 10 to the 12 dimensions. So we can take advantage of the fact that what you see here is that the integrand, this thing, really has this weight factor here, which doesn't depend on what observable you're trying to calculate. This weight, this e to the minus s glue and the det m, that's the same no matter what observable O you put in here. So we can sample contributions to the integrand, so sample this space of configurations with this weight already built in. So that's called importance sampling, with the goal being that you, of course, sample the most important contributions more and the less important contributions less, so that you don't, you know, blindly sample the space, then have a large part of that space just made irrelevant because it's significantly downweighted by this factor, which is in every interval that you might want to calculate. So, because the integrand has this weight.
No, yeah,
Oh, sorry, is there a question?
go on. There's a couple of questions.
Sorry, I had a question about the indexing on the link variables.
Same question.
Is for the gauge fields, A was running 1 through 8 because it was indexing the generators of the algebra, and now U's are the group elements, right? So there should be matrices. Or
Exactly. So I sort of skimmed over the details here on how we went from, you know, how we moved to our group elements from our generators, but we're coming back to that. But you're exactly right.
thank you.
I have a similar indexing question. The mu, so on the A mu, that's the Lorentz index on the gluon
That's
field.
right.
Is it the same? What is it? But when it's on mu, well, on U, is it still the Lorentz index? Because then you said it's the direction.
Yeah. So when we identify these U's as our parallel transporters, you can really think of associating each U with an edge of your hypercubic lattice. So then that mu, you're right, it came from that Lorentz index, but now we're going to interpret this U mu as sitting along the mu direction here on this lattice grid. So if you were doing a lower dimensional field theory, you would have your Lorentz index running over fewer numbers. It wouldn't be 4 anymore, and you would have fewer directions here. And so it all works out no matter what dimensionality you're sitting in, right? So it's sort of both. It's the Lorentz index and also the direction in your hypercubic grid here.
So it's one of the 4 directions in your Euclidean space.
Exactly.
Okay, and you're just saying here that every operator that you build that you're going to compute has to be built out of gauge invariant things. So you're just going ahead and writing everything in terms of gauge links from the beginning.
Well, you can make non-gauge invariant things out of gauge lengths too, right? You can compute non-gauge invariant things in some fixed gauge in Lattice QCD, but you can write them in terms of gauge lengths, even if they're not gauge invariant. Right, so we'll come back to where these U's come from when we try to discretize. So if you think about discretizing the fermion action is probably the easiest way to see it. We're going to have our covariant derivative in there, right? And in the continuum, you get the gauge field from writing the covariant derivative, and you try to make it covariant, so you end up with this gauge field here, right? And the same thing is going to happen on the lattice. When we try to write down our discretized derivative through a finite difference, to make that thing transform the right way, you're going to have to put in a parallel transporter. And so that parallel transporter looks like this, and it's holding those same degrees of freedom, A nu, as we had in our gauge field. So that's how we basically make that shift to the group elements, is by realizing that we need the parallel transporter to make that action work.
Okay, thank you. Any other questions right now?
I do, but she might be about to answer it. So
Okay, we'll ask at the next pause then.
sure.
Go on, thank you.
Okay, so the integrand, as I said, has this weight factor. We've got e to the minus s blue det m, which all depends on that u, right? So the way we can do this integral, this, as I said, very high dimensional integral efficiently, is we can sample the space of all u's according to this weight. Treat this as a probability measure. Okay, and we don't have time in these 3 hours to really get into details of algorithms, but you can do this. One way of doing it, the normal way is to use a Markov chain process. So you have one of these gauge field configurations, one of these U's in the space of all U's that you want to sample over, and you update it in a chain through Hamiltonian dynamics. So you're basically making a small change from one configuration to the next in the chain in such a way that you'll know that in the limit of a large number of samples, you get the right probability distribution. So a Markov chain Monte Carlo process, which I'm happy to talk about, but so you can do this via some Markov chain. So you're basically stepping between configurations in such a way that the transitions are defined to satisfy conditions of ergodicity and detailed balance. So that you get the right probability distribution. As the equilibrium distribution. So typically we'll use, like I said, hybrid Monte Carlo or Hamiltonian Monte Carlo, which is just where these transitions are defined using Hamiltonian dynamics. And so then typically you'll make that that update through Hamiltonian dynamics, but the fact that you have a numerical integrator means that you don't have exact energy conservation. So then you have to do an accept reject step to fix up the fact that it's not a perfect integration and so on. And so you generate this ensemble. And so then once you have a representative set of samples through this process, so you have a set of these U's, and they've already been sampled with this weight built in, then anything you want to do, any observable O, you just compute it. U goes in there. You might need to calculate some M's, but each M is just a Dirac operator inverted on that U. So you just compute this thing on each one of those samples, take the mean and the standard deviation, and you have your central value and uncertainty, essentially. We'll go through a little bit more detail in that in the next lecture, but you can reuse that set of samples for whatever you want to calculate. So we have a representative set of configurations, which is called an ensemble. Observables can be computed. As simple averages. And uncertainties fall with the number of samples that you take, of course. So you've got expectation value of some observable is going to look like your average over the number of configurations you've got, plus some uncertainty that goes with square root n as the number of samples increases. So then a complete calculation, of course, means that you need to deal with statistical uncertainties. More and more samples, statistical uncertainty gets smaller and smaller, but also the systematic uncertainties. So ideally, you need to do multiple different values of the lattice spacing, multiple different values of the box size, and take all of those limits to get back to continuum QCD. But you have to do a separate calculation, right? If you change the lattice volume or lattice spacing, you have to go back to the start. You have to generate a new set of samples, you calculate all your observables. Okay, so this is pretty much the core of it, right? So where we're going to go from here is I'm going to talk about, well, how we actually define the lattice actions, which I thought I'd get to all of this lecture, but we might not get quite through it. And then a little bit more about how you actually go about calculating an observable, and then some intuition on, what types of observables are easy, hard, why, what are the typical scales. But so this, we've sort of got the main idea already. So any questions about sort of how lattice QCD works at this broad scale?
Yeah.
Andrew has a question.
Yes, I have a question. So I've heard physicists complain about certain actions not being easy to quantize in path integral formalism. And then I've also seen mathematicians complain about the existence of a path integral in the first place. So my question is, are those two complaints the same, related, unrelated?
Okay, so you need to point me to what you mean by the existence of a path integral in the first place. Can't comment on that. Some actions being harder to quantify than others, that is certainly true. So I'm hoping to have time to get to some of the choices you have in fermion actions and some of the challenges you get. So what we'll see next is that if you try to just write down a fermion action the most naive way, that it doesn't really work, that you get something that does not have the right continuum limit. You get, you might have heard of the doubling problem, that you actually get a whole bunch of extra species of fermions that aren't coupled to the others. And so the action that you write down just isn't the same. And then there's something called the no-go theorem, which says that it's not possible to make a lattice fermion action that's ultra-local, chirally symmetric, undoubled, and has the right continuum limit. So yeah, at least we don't know how to write down an action that has all of those properties. So certainly if your question is about some actions being harder to disclose than others, that's true.
And yeah, maybe I was too loose with the existence part. So what I mean was you were able to identify the measure with something probabilistic because you were able to Wick rotate and identify like this this measure with effectively, I think it's called the Wiener measure, if I'm not mistaken. And then like you said, you're able to identify like the generating functional with like the partition function and things. And I thought that is what made the path integral defined in like simple cases like a harmonic oscillator or something. But I thought when you went to more general cases, people would take out pitchforks when it came to defining the measure. So I was wondering if those two complaints were related about quantizing the action and the existence of the measure, I suppose.
I don't think they are, no.
Does the latter part of the question make sense at all of existence? Because
Well, mathematicians will complain about everything we do in quantum field theory. So
Yes.
let's not go there.
Showing that that integral gives a number is very difficult, actually.
Yeah.
Taking continuum limit.
You can point me to these complaints, then maybe I can comment on them, but I haven't read what you're talking about, so I can't say anything.
Okay.
I don't see questions here right now.
There is one in the chat.
There's no one.
Okay, so
Can you read? Actually, you're welcome to unmute and ask the question as well. Or just have the lecturer read it.
let's take someone smarter than me. This.
I was just saying that sort of a comment in response to Andrew's question. You brought up the Wiener measure, and that works for non-relativistic quantum mechanics because you're sort of doing zero-dimensional field theory. But when you take that integral over the field at each point in space-time, if you try to take the continuum limit, you need an infinite dimensional Lebesgue measure, and that doesn't exist. So people have tried doing other kinds of measures, but typically they're sweeping under the rug that the fundamental measure they have doesn't exist. So that's an open problem as far as I know.
Thank you for specifying what I was trying to ask. Appreciate that.
Okay, are there any other questions at this point? Okay, cool. So we have like 12 minutes to get through lattice actions. Okay, so.
About 15 minutes.
Okay, excellent.
17 to be precise.
Okay, so like we said before, in continuum field theory, you really get the existence of the gauge field by demanding gauge symmetry, right? And then you demand gauge symmetry. That means that you have to have the existence of an additional gauge field to define the gauge covariant derivative. And so just everything pops out beautifully, and scalar QED or whatever examples you used in a class. So the same thing happens in the lattice formulation. It just looks a little different. So let's just start with the Euclidean Dirac action. Okay, so we've got d for x, psi bar, d slash plus m, and we're Euclidean, right? So no i's, psi. Okay, now the most straightforward way to discretize this would be to say, okay, we have a derivative, so let's just do a symmetric finite difference. And we ignore the fact that this is gauge covariant, right? Just think derivative goes to symmetric finite difference. That's the most obvious stupid thing we could do. So So if we tried to do that, you would start writing down something like this. So remember that our fields are defined on the sites n. So we're going to write down sites n again. Where this notation that I'm using, n plus mu hat is saying we're shifting lattice site by one site in the mu direction. And similarly here, shifting from n to one site in the minus mu direction, where we're using, say, mu as some of the directions in our hypercube. And this thing here, of course, is not gauge invariant, right? So this is not a good thing to do. So if we remember what the gauge transformations look like, right? We had our psi goes to some transformation, some SU3 matrix times psi, and similarly for psi bar. Okay, so just in the way we introduce a mu to patch up the covariant derivative here, we can introduce the gauge links as parallel transporters to make this expression be gauge invariant. So we can introduce okay, so if we write down our parallel transporter, it transforms like this. And then if we replace this term in our finite difference with the same thing, but with a u plopped in, that's the parallel transporter between n and n plus mu, of course, but by construction, because it's a parallel transporter, this thing will now have the right transformation properties, right? So let's replace okay. So then we have something that looks like a derivative and is also gauge invariant. So let's think a little bit about what these gauge links are. So really, they're special cases of parallel transporters. What a parallel transporter is in general, it maps coordinates in internal symmetry space from one point to another, right? And so another way of writing that parallel transporter is like this. So as a path ordered exponential, if we Taylor expand in the lattice spacing, we're really talking about a translation between the group and the algebra, yeah, right? So what we can identify is this gauge link that you write it down as a parallel transporter from site n to n plus mu. You write it down as the thing that has this transformation property that you need to make the finite difference gauge invariant. You can identify it with the links of your lattice. So if this is n, the link u goes to from n to n plus mu. Okay, so what about, if I wrote down u mu dagger n. What's another way of writing that without the dagger? Or what does a dagger do to this link here even?
Reverses the direction.
Exactly. The dagger changes the direction of that arrow there, right? So it would be still going between n and n plus mu, but going in the opposite direction, right? So another way of writing that is stepping in the minus mu direction, if you like, from n plus mu. Right, so still the link from either n to n plus mu in the forward direction, or the link from n plus mu to n in the minus direction. Okay, so if anyone, if you hear that in lattice field theory, the fermions are on the sides and the gluons are on the edges, that's all that this means, that the fermions are discretized to be defined on the sides of the lattice, and the gauge fields are identified with these parallel transporters, so you can think about them lying on the edges of the lattice. Okay, so doing this, we then get a naive fermion action, if you like, is the simple thing we can write down. So and the naive fermion action is not good. Okay, so let's just write it out and then we'll see why this breaks. Okay, and so let's just rewrite this. So this was the form that we wrote this in before, when I said that we can rewrite the action into a quadratic form, right? And you can go through and you can write out explicitly what this thing here, you could call that the naive interaction matrix, you could call it the Dirac matrix, however you like it, just by pulling out, this psi bar n on one side and the psi n on the others, and putting in the appropriate form of the matrix to make it look quadratic like this, right? Okay, so this tilde here is up to factors of a. There's some factors of a out the front here, a being the lattice spacing that I wasn't careful with in writing out that expression. But otherwise, all I've done is substituted in these parallel transporters to make this thing look gauge invariant. Okay, so looking at this lattice action, naively it looks okay, right? If you Taylor expand the whole thing, so Taylor expand the fermion fields, Taylor expand the gauge links, all in powers of a, that's the lattice spacing, what you would find is that this looks like the continuum action up to order a squared. So what you would say is that this action has order a squared errors. So a being the lattice spacing, obviously you make the lattice spacing smaller, the a squared errors get smaller, you get closer to the continuum. And so this really gives you a hint of comparing different lattice actions. Some lattice actions might have order a errors, or order a squared errors, or order a4 errors. And so you can see, which ones are going to be worse at coarse lattice spacings and which ones are going to be better already at coarse lattice spacings. Okay, so this has order a squared errors, which sounds not bad, but it has this doubling problem that we already mentioned before. So basically the doubling problem is that this first order derivative here, it's only coupling sites that are separated by 2a, 2 of the lattice spacing, right? It's just a finite derivative. And so what that means is that in the continuum limit, you have these different sectors of the lattice that are separate from each other. So you end up with copies. That's why it's called a doubling problem. And you have 2, because they're separated by 2 to the power of the dimension. So that's in 4D, that's 2 to the 4, that's 16 quark flavors instead of just 1 quark flavor. So it's not the same as what we want in the continuum, which has just 1 quark flavor. If you want to really see that explicitly, you can look at the poles of the inverse free 2-point correlation function, or the inverse fermion propagator, if you like. And what you see is that it has poles, if we take mass equals 0, poles not only at momentum 0, but at all of the momenta which are like, 0, 0, 0, pi over a, or pi over a, pi over a, pi over a, pi over a. So all of these 16 different momenta with pi over a in every possible place there all have poles of that inverse fermion propagator. And so you can see exactly where that doubling comes from, if you like. But for the purpose of this lecture, we just have a doubling problem. And the easiest way of seeing it is, I think, that those different, the quarks being coupled only 2 sites apart, that doesn't go away in the continuum limit. They're still only coupled 2 sites apart because it's still your finite difference. Okay, so this then brings us to, well, really the no-go theorem, that it's not possible to construct a lattice fermion action that has all of these properties that you'd like, that it's ultralocal, chirally symmetric, undoubled, and has the right continuum limit. So there are different choices you can make to get around it. And so you've probably heard of some of these different types of fermion action. You can choose, say, Wilson fermions, where the idea is that you break chiral symmetry explicitly, even when the mass is 0, by adding an extra second derivative term. And it basically acts as a large mass that drives all of the doublers up to high energy, where they're not going to get in the way of what you're trying to calculate. So you get rid of the doublers, but it introduces order A discretization errors. So then you've got worse discretization errors again, which you can try to fix, and it's at the expense of breaking chiral symmetry. You could do staggered fermions. So for staggered fermions, you put the 4 different components of the Dirac spinner all at 4 different lattice sites. And then the consequence of that is that you get 4 different species or tastes, and then you can break taste symmetry. So you sort of solve one problem at the expense of another. Or you can do different types of Ginzburg-Wilson fermions, which preserve a lattice version of chiral symmetry, so not the continuum chiral symmetry, but what's called the Ginzburg-Wilson relation that reduces to the usual chiral symmetry in the chiral limit. But then the downside of those is that they're all computationally more expensive. That's things like domain wall fermions, overlap fermions, things like fixed point fermions or perfect actions. And so you have all of these different choices to make here on how to avoid this problem, some of which sacrifice different things like chiral symmetry, some of which sacrifice things like computational expense. So let me just very briefly note, so no-go theorem and so what you get is choices. And which one can depend on the particular application. Like, is the computing cost really an issue, or do you really care about chiral symmetry? And that will depend on what you're trying to calculate. So I mentioned Wilson fermions. I mentioned staggered fermions. I mentioned Ginsburg, Wilson fermions. So domain wall. And so on. Okay, so when I mentioned Wilson fermions, for example, I said that adding in these extra second derivative terms basically gives you order A discretization errors, which sounds worse than what you have from the naive fermion action, which is order A squared, right? So there's a whole type of improvement called the semantic improvement program, where what you do is you basically add additional things to your action, which cancel out the leading discretization artifacts. So you add extra things, with coefficients exactly tuned to eliminate those leading order A or order A squared or order A cubed effects. So if someone tells you that they're using a HISQ action, HISQ, that's highly improved staggered quarks. So they're using a staggered action, but it's highly improved. So they're adding a bunch of extra terms to the action to cancel off leading discretization artifacts. And so all of the various actions are sort of constructed from these. And I'll add a few more notes about what each of these are in the notes that I'll post later. Okay, so the last thing that I wanted to do today, but we're out of time, aren't we? Was talk about the gauge action, but I can start with that tomorrow.
Yeah, I think that's a good place to break. So let's thank Phiala for the first lecture. Open for questions if there are any. Insists on knowing about the gauge action before going to lunch. In here. On Zoom. Everyone's happy on Zoom, looks like. Yeah, so we can start